So have you ever wondered how much energy a satellite has as it orbits around a body? Well, if you have, then this video is perfect for you. So what I'd like to consider is the total energy of an orbiting body around a planet in terms of its kinetic potential and therefore total energy. So here I have a planet of mass big M, and we've got a satellite of mass little m, which is orbiting around it in this nice circular path. Now this is going to be a distance of r away from the centre of that planet. So the distance between the centre of masses is equal to big R. Now, first of all, maybe let's consider the potential, okay? And the gravitational potential, which is Vg, we always use the symbol V for potential, is equal to minus Gm over R. Okay, so that's the amount of energy per unit mass that this has. If we want to actually find out about its potential energy, then that's going to be equal to the energy, the total energy that it has. And that's equal to effectively the mass times the gravitational potential, which is going to be equal to minus Gmm over R. So this here is the potential energy of that satellite at any point. And as it gets higher and higher and R gets bigger and bigger, it has less potential energy. Now, in order to work out the kinetic energy, we need to know how fast it's moving. And what we can say is that at any point it's moving with this tangential velocity of v. So we can do this by basically equating the centripetal force with the force due to gravitational attraction. And what we can say is then that the centripetal force, which equals mv squared over r, is equal to gmm over r squared. So that's from Newton's law of gravitation, that's from our centripetal force, and that's basically, because it's acting inwards, it's this force, this kind of positive force, which is providing this. What we can then do, we can cancel out the m's, and we can cancel out one of the r's, and we can also write this as v squared is equal to gm over r, or indeed we could say that v is equal to the square root of gm over r. In order to work out its actual kinetic energy, Ek, well, we know that Ek is equal to a half mv squared, which is therefore equal to half times m. Well, v squared is equal to gm over r. And I can also write that as equal to gm m over 2r. So this here now is the kinetic energy, whereas that was the potential energy. But what about the total energy? Well, I'm just going to call that ET to be my total energy of this satellite as it's going around. And this is basically equal to the sum of the kinetic energy added to the sum of all the potential energies. And the Ek is equal to gmm over 2r. And we add that to this value here. Now that's negative, so that means that's minus gmm over r, which is therefore equal to minus gmm over 2r. So this is the total energy of that satellite. Now at the moment it doesn't really make much sense. As far as I can see, it's just some different equations which look quite similar. So it's probably sometimes more useful to think about this graphically. So if we have a look at the graph which is just over here. So this graph here has our energy on the y-axis, and on the x-axis what we have is the distance of r away from the centre. Now obviously we can't really go any closer than the surface of that. So first of all, if I plot the potential energy, what we get is a curve that looks a bit like that. Okay, it's always negative, and as r gets bigger, we find that this value of EP goes down and down and down. Also, if we then maybe look at the kinetic energy, well, it's going to be half as big, so when that's this distance, this is going to be up here somewhere, but this time it's positive. So what we find is, if I just get that curve in, we get a curve that looks a bit like this. So this one here is my kinetic energy, this one here is my potential. And kinetic energy is always a positive value because, you know, V is squared. What's the sum of these two things? Well, it's basically this line here, over here. So this is my total energy. And what this basically says is that the further away a satellite is from that planet, the less energy it has. And effectively, when R gets really big, so as R tends towards infinity, we find that the energy of that satellite tends towards zero, which is what we see over here. So I hope that helps. This is just about really sort of some algebra showing the total energy of a satellite that is orbiting a planet. Thank you.